Okay, let's address how to set up this case, particularly the production limiter. So here, already load the case. Remember, it is a 2D case, so when launching Fluent, remember to open 2D case. Just to remind you that I'm working with the pressure-based high-speed case, but then you have the other two, so the setup is similar. Requires for use your new density-based solvers, be careful that the tune is a little bit different how to set up the solver. I'm not going to address that, but my advice is stick with the pressure base, okay? So at this point, let's see how to set up the case. Where's the deal here? So again, see, we have, this is our mesh, okay? So we have, if you want to extract the airfoil coordinates from the mesh, remember that you can do it here, extracting coordinate, there is no problem. So this is a relative nice mesh, and see that in particular this is a wall modeling mesh. Okay, you see that it's not as fine as the previous one, but still it is a nice mesh. Okay, we have a nice transition, and as we saw in the introduction, maybe here is where we have a little bit diffusion, okay, when interpolating the viscosity, that stuff. But for the rest, this is okay. This is very nice. So now let's see how to set up the case. Okay, so again, this is the vertical workflow, and in particular, let me go here in the viscous model. Okay, so look at here that in viscous model, and now we're going to talk about these options. Okay, these are to correct the deficiencies that we have in turbulence model. Okay, in particular, there are two important ones, that is the curvature correction and the production limiter. In this case, we're going to address that one, production limiters. And see, by default, the production, there are two production limiters, okay? But see that one is enabled by default, and it will be the same in the turbulence model. Okay, so K exiting is not enabled, so I don't recall, probably change it, but I think if you start from a clean setup, it will be enabled by default. But if it is not, enable this one, please, okay? And then the Spala Armadas is the same, okay? So this one, okay, you have it here, it is already included, okay, in the formulation. Okay, and the same will be with all any other turbulence models that it has this deficiency. You will have the option to enable that. Then you have a second one that is called the production cathode limiter. So as you recall in the transition cases, these two were enabled. Okay, so this is another one just to improve even more your results. Okay, to reduce that overproduction of turning kinetic energies in stagnation points. Okay, so let me run this case, and I will disable both of them. Okay, by the way, if you enable this, once you go here to the button, you have this clip factor. Okay, this is the one that you use to control that limiter. Usually the default value is 10. Okay, so if you put it to 0, you are disabled that limiter. 10, you put it to you use the default values, and you increase it, and you are adding less limited, let's say, yes, less limited. Okay, so careful that 0 is not equivalent to switch it off. Okay, 0 is you put it to 0, it will not produce any TKA. Okay, be careful. So you can play with this one, but again, just use the default value. Okay, so leave it like that. It's completely switch it off. Okay, so we have, it is compressible, so it shows the energy. Also, there are a few additional corrections, viscous heating. Okay, so you can compressibility effects. So press help to read about this. I'm not going to address this correction. It's just related to high speed flows. Okay, then we go materials. Okay, just to address that we're using air, but now here that we have ideal gas, suture and low for the viscosity. Okay, so it's temperature dependent, those also top everything. Then go for boundary conditions, and we have here our setup, and see that in this case, in this setup, we have a far field, okay, which is all this boundary here. Okay, so see that far field in, far field out. And recall that we have this very helpful boundary condition, pressure far field. So as you set up that here, see that you just give the Mach number and your incidence angle and reference pressure and your inlet value, no boundary conditions. So this is our standard setup, nothing to do here, reference values to normalize coefficients. And now we go to the case setup, the numerics. Okay, so now we address everything here. Okay, so I invite you to revise everything, and if you want, you can do some modifications. Remember that if you change the incident angle here, you will need also to do the correction when computing the coefficients. Okay, this is just to change your reference system to compute forces. Okay, so we're using default method. Okay, default control values here, report definition. See that we set up y plus average, okay, and CD. So if we take y plus average, okay, how computed, but how it's computed, then see that I click here CD and see that I have this transformation, okay, this rotation of my axis to compute the forces in the right reference system. Okay, be careful about this. Okay, it is in the slides. Okay, so then nothing else to move here. Okay, so residuals, plots. I think here I set up a report monitor. Okay, so you have it there, and now we can initialize. So let me initialize. So I'm going to start from scratch, and also I will use a better initialization. Okay, instead of using this one, okay, I will go for a full multi-grid initialization. So this is a uniform initialization. So if I plot here the results, see that everything is uniform. But as you go here to your text user interface, see that I go solve, init, and here now I have this option, FMG initialization. So this is a better initialization than the standard one. Okay, so it is running. Okay, it's kind of computing a fast and expensive iteration to get a good feel. So see that now, if I plot this one, see that this is much better than a uniform field. Okay, so we have this, and you will have the same for temperature field, for everything, pressure. Okay, so let's use this one, which is a better condition. And at this point, I think I'm done. Let me press calculate, and off we go. Yes, to override whatever we have. So see that we're computing CD, CL, okay, maximum Y plus, everything. Something that I want to mention also, to give you an advice also, is you are running 2D cases and steady simulations, my advice is to go ahead and have super fine meshes, okay? Because you see here, these cases are very inexpensive, okay? Instead, if you have 3D cases, you should assess, look for your resources, see, estimate your time. But in 2D cases, don't be afraid, go ahead and use very, very fine meshes, okay, in the distant normal to the wall, okay? So don't be afraid about that. So we have all our residuals. See that we have a very nice convergence rate here. CD is already kind of, okay, becoming stable. And actually see that the solution for report definition has converged, okay, the one that I defined here. But my residuals, it's still, they haven't converged to the desired value. But at this point, we can say that this is a good solution, and see that our Y plus value average is just about 48, okay, which is okay. Okay, wall modeling, this is a very nice value. I recommend you to have this value about between 40 and 100, okay, it's a very good choice of value. So at this point, let me stop the simulation here. I know it's not going to converge, these are installed there. So let's visualize our solution. See what we have here. We have the shock wave. You see clearly here. So see that the method is shock resolving. Okay, it's resolving that, but also you can use adaptive mesh refinement, as we did in some previous tutorials, to capture that one. I'm not going to do it. Okay, it's up to you. But see that nicely resolved. Okay, your velocity. Okay, well, probably here we can put the pressure contours. Okay, so see that, see there. And now let's take a look at the turbulent viscosity. Okay, and just to mention about again the mesh quality, these mesh issues. Okay, so usually, as I say, this is a good indication to see if you have a good transition. Okay, so usually remember that when you have the maximum of the turbulent viscosity or the turbulent viscosity ratio, you should have a good mesh, a good transition. Here it's not easy to see, but let me change the scale. Okay, so still here. Okay, so see that turbulence viscosity ratio here is peaking in your boundary layer about the middle. Okay, you have a peak there, and see that it's okay. See that we're kind of capturing. It might be better to add some other layers, but this is okay. It will be different, for instance, if you had here this separation now between these values. You have this here in this cell, the triangular. That would be bad, okay, because these cells are not very good to resolve these step gradients. But in this case, it is nice, okay. So I recommend you always to take a look at this turbulent viscosity. Okay, it's a very good indication to see if you have a nice mesh. In particular, in this case, what we're interested in is in the turbulent kinetic energy production. So let's plot this. So in particular, let me just plot the turbulent kinetic energy. Okay, so see that we have this, and let me change the scale. Okay, so in this case, I think I leave the limiter on. Okay, let me go back to this dice to see the range was, okay, 0 and 10. So yeah, let me reduce it a little bit more. Okay, so see that we have this, okay? So see that usually in stagnation points, we might have overproduction. So in this case, okay, if I go back, should be on the limiter. See that it is on. So see that that one here is avoiding the overproduction of turbulent kinetic energy. So if I disable this now, and let me run a few iterations. So again, see that you have a jump there. So see that there is an influence in the numerics, okay? So I disable that, let it run for a few iterations. Also, you compute your forces, you will see that it's an influence there. Okay, maybe there will be a slight difference. And it's running. Let me stop here. That I think is already okay. And if I plot here, see what we have. Okay, clearly see that this is when I talk about overproduction. See that you are producing too much turbulent kinetic energy, or who knows if it's too much or too low. Okay, but as you compare with the limiter on, see that clearly you have here an effect, okay? And see also that where you have the chop wave, you have this also producing some turbulent kinetic energy there, okay? So this is the idea of this production limiter. So when you enable the production limiter, now we're going to see that this effect is not going to be there anymore. Okay, so let's run again. So see that you see an effect on the numerics. Let's run again a few iterations here. Okay, so my coefficients are okay. And let me stop there. I think it's already okay. And see that now clearly we have the same range of value. Okay, remember, and see that it disappear all that overproduction. Okay, so this is the idea. Okay, usually something that you are going to see where you have in the boundary layer where you have a strong gradients, or in the shear layer, okay? And let's run again, let's keep running, and let me enable the second limiter, the cathode limiter, and say launch. See that again, a jump there is some influence in the numerics. And let's wait a little bit again. When you run this one for you, just check the coefficients, okay, and compare. Remember that we have these experimental values, and quantify the error, okay. There is a difference, not too much, but the most important thing is the influence now in the field, in the whole domain. Okay, so at this point I can stop it here. And if I plot, again, we have this. It's different, it's difficult to know now what is happening. We need to compare now with the other case, with the much different scales, but you see that there is a clear influence, okay? So this is for this case. Again, we have also, we can take some measurements there. So you have the CP, okay? So plotted in the surface, you have the validation data there. So you can go here and, okay, show it here. And we have CP. And if I plot here, see that we have a quite good agreement. It's set here where we have the shot wave, but there is a problem of mesh quality, okay? There would be better to increase the mesh quality precisely in this region where we have the shot wave. That is an exercise that I leave open for you, okay? Then also we can compare friction coefficient. Okay, see that we have this both on top surface. So in this case, we're not interested in transition, and actually there is no transition here. Remember that shockwaves also can unset transition to turbulence, okay? But here, let me plot here, we have this, and we have some data that we can compare and see that, yeah, I don't recall this data, it should be probably the bottom surface, I think. But see that we have some good agreement there, okay? Or at least it's following the trend of that data. Again, finally, remember that you can plot that normalized velocity profile, okay? So let me go here. So you can pick up a line and plot that, okay? So you can plot it here or here. Avoid to plot that in the precise region that you have the shock wave, okay? For obvious reasons. But you can plot it here. Remember, it has to be where the flow is fully developed and fully turbulent, okay? And you should be able to get the similar profile, theoretical profile. See also that the shock wave, there is an interaction between boundary layer and shock wave, okay? There is a lot of literature about that, but see that here clearly you have this interaction. It kind of inducing some separation here. Okay, so maybe, let's see what happens if I plot some vectors there. And let me scale. Okay. So yeah, there's no separation, but there is an influence. Now it makes the boundary layer thicker there in that region. Okay, so I think this is all for this case. I just, as I say, probably just for completeness, just to show you, for instance, let's run for these parallel matters. Okay, here we don't have the production limiter. Okay, so let's see what happened in this case. If I were to recall, the implementation already has a correction now to avoid this excessive production of total kinetic energy. I need to read the documentation, don't recall. But also remember that these limiters, you have it in the linear eddy viscosity models, okay, those models that suffer of this. So for instance, the Reynolds stresses model, you don't have that, or nonlinear eddy viscosities, you don't have it because those corrections are already done now, because now the viscosities are anisotropic, so there is no need to add this correction. So let's see what happened in this case. Okay, let me go. Turbulence should be okay. So yeah, we are not going to see the total kinetic energy because remember, in the parallel matters we don't compute that quantity. Okay, so yeah, that's why there is no production limiter. Okay, so it's not computed there, but you can check it also. You can compare, for instance, if you get the total viscosity ratio, you can compare those ratios, okay, and see how they differ from the solution of the K omega family. So this ratio here was 0 to 500. So let's see what happened here if I go to similar ratios, okay, So see, this is what we have. It's something that appears to be very similar. Okay. So again, you have that there that you can use it to compare cases. So that's all for this case. Okay. So you have a lot of to do here. Okay. So you have this exercise that you can try the different models here. Also, you can try different models, K epsilon or K omega family, enable this limiter. Okay, you can play around to reduce or increase this value. I don't recommend you to move it because 10 is a good value, has been calibrated. Okay, and also you can try to do the plot of the normalized velocity. Okay, that shouldn't be that difficult. So that's all for this case. Thank you very much for your attention. See you next time. Bye.